Okay, so this is the outline of chapter 27. So we only talk about single loop circuit, multi-loop circuit, or ammeter, voltmeter, and also the RC circuit. Yeah. So for the single loop circuits, so it is as simple as this. We have a battery, we have a resistor in series, and that's it. So it is quite stupid. Maybe you can just assume this point is a ground. So this is the potential here is 0 volt and nothing else. So you can see as much as this is a battery or a EMF device, which means that the voltage here, this V is nothing but E. And then we will assume that the current is clockwise. So this is also V, which means that we should have something like E equals IR. So V equals VR, which means that VR equals I times R. So it is as simple as this. So I don't think I need to talk too much about that. Okay, so another idea is that we talk about ideal EMF device and also real EMF device. So for ideal EMF device is one that lack any internal resistance. So the potential difference between its terminal is equal to EMF. Okay, so of course in the real world it does not exist. For example, for your mobile phone. So if it is fully charged, the battery has a higher voltage. But if you consume some of the electricity, then the voltage of your battery will decrease. So it means that if it is an ideal device, we just assume it to be something like this. Then it is a ideal EMF device. Or sometimes I may draw it like this. So these two symbols means the same thing. So in circuit theory, I usually use this notation rather than this one. Okay. So for ideal EMF means no matter what it connects, the voltage across the EMF device doesn't change. So it doesn't really relate it to what the current is. The current is positive, negative, it doesn't really change Vs. So if we just try to plot it out, so if it is an I, it is V, then it is all the way Vs. So for the ideal device. For real EMF device, it has internal resistance, which is the practical case. So the potential difference between its terminal is equal to the EMF, not only if there is no current through the device. So in circuit, we can connect it is a ideal battery in series with a small resistance. It is something like this. So which means that if I is larger, then there will be more voltage drop across the internal resistance. And this whole thing we consider it is the real EMF device. So if I just try to plot out the IV characteristic, which means that if I is 0, it is the same as Vs, but there will be a negative slope here. So this is like negative R or negative 1 over R. Okay, so which means that if I is 0, we have this one is Vs. So here, it really means that if we have this is Vs, this is R, and this whole thing means the V we are plotting. So this is the case. So in circuit theory, we usually use this kind of notation, which means that we draw a symbol, and then the plus sign means the potential at this point, and then the negative sign means the potential at another point, and then we try to subtract this point with this point for this potential difference. Okay, so if I is larger, there will be more voltage drop across this R. So it turns out V will be smaller. Okay, it is something like V equals Vs minus R times I. So this loop is a negative R. So when R equals 0, which is actually the same as the ideal case, but unfortunately, usually it will be larger than 0. Okay, so here it just tells you E equals IR, or you can use the energy method for it. So it is the energy equals another energy, and then take the derivative, something like that. So for this case, it is quite dumb, I think. But maybe in the next chapter, when we use the energy method, it is a bit interesting. So maybe I will go in deep about that later. But here, it is nothing but E equals IR, because it is still the same circuit with different approach, the energy method and also the potential method. Yeah, still the potential method is nothing but E equals IR, so nothing special. Okay, so in the textbook, it tells you that we have the loop rule. Okay, so but actually in circuit theory, we will call it KVL, Kirchhoff voltage law. Kirchhoff voltage law. And another rule is called the KCL. I think I have already mentioned it in chapter 26. So at that time when we talk about if we have a node with multiple connection, then it says that all the current going in a node sum up to be 0, which means that the current going in a node equals to the total current going out from the node. But KVL means if you just find a node at a circuit and then you go for a loop and go back, then the potential changes will sum up to be 0. So it says the algebraic sum of the change in a potential encounter a complete traversal of any loop of a circuit must be 0. Okay, and also resistive rule is nothing but the Ohm's law, E equals IR, and the EMF rule is like the EMF will generate some voltage difference. So nothing special. Okay, so here if we consider the internal resistance, just like what I mentioned, this is the real resistance. So we model it as an ideal battery in series with a small resistance. Okay, so in that case, the total resistance of a circuit will be R plus small r. So which means that we should have E equals I times small r plus capital R, like this. So still nothing special. So the only difference is that the internal resistance makes the current smaller, because part of the EMF is absorbed by this internal resistance. Okay, so for similar thing, if we have serial resistor, so which means that we just add the resistance together. And if we have parallel resistance, maybe later. But yeah, so I think resistance in series is trivial, so I don't go through the procedure, because it is just like R1 plus R2 plus R3 is the equivalent resistance. So if we have series resistance, you just add them together, and this is the answer. Okay, and here potential difference. Yeah, potential difference. Potential difference is just like you subtract the potential for the two different points, so it is nothing special either. So maybe let's stop here today.